Welcome to your video on solving systems with special solutions. Now, what we mean by special solutions are things like either no solution or infinitely many solutions. So you've actually seen these before a little bit. We're going to get started by working on an example here. And the directions say to solve the system by graphing and elimination. Now, we've just been working on elimination, and this one is set up really nicely for elimination, but we're going to go back and start with graphing. So our first equation there is not in a good form for graphing. So what we're going to do is get y by itself. The first step is to move the x to the other side. So we're going to accomplish that by adding 2x to both sides. Now remember, we can't combine the -4 and the 2x. Those are not like terms. So we just put them in slope-intercept form and say 2x minus 4. And what a lot of you are doing is identifying the slope. So m equals 2. And some of you might want to say 2 over 1 so that you get the rise over the run. And then our y-intercept is at 0, -4. So B for begin and M for move. We're going to begin at 0, -4. So go to the y-axis, down 4 units, put your y-intercept. And then our slope is 2 over 1. So we're going to go up 2 over 1. You're going to do that as many times as you can. And obviously with the smartboard here, we get a little bit off. Yours should be right on, and you should be using a straight edge. So we're going to go ahead and graph that line and move on to our second line. We're going to do the same thing over here. We have to get y by itself, and so you'll see the -2x plus y equals 3. What we're going to do is we're going to add 2x again. That leaves us with y equals 2x plus 3. So our slope is identified as 2 over 1, and our y-intercept is 0, 3. We go to the y-axis, we go up 3 units, put our point, and then we again count our slope, up 2 over 1, as many times as you would like. You can probably already see what's going on here. Because these two lines have the same slope, they are actually parallel. And you don't write parallel as your answer. Remember, we're looking for the point where the two lines intersect. So since they are parallel and will never intersect, the answer is no solution. Now you may be thinking, I already know this. Why are we going over this again? Well, not every problem is going to be solved by graphing. So now we want to look at what happens if we're using either substitution and elimination, because we don't have that picture to look at. So we're going to go back to our original problem. In fact, if you just want to recopy it on your note sheet where you have a little bit of extra space, we'll note that it's set up perfectly for elimination. The x's are lined up, the y's are lined up, the equal signs are lined up, and the numbers are lined up. The only problem is it's not ready to go. If we add them together, nothing's going to drop out. If I change one of the equations just by multiplying by a -1 though, we should be in business. So we're going to multiply that top equation. When we distribute the -1, we get 2x minus y equals +4. Now I can go ahead and take that bottom equation that we didn't change at all, along with the top equation that I just multiplied by a -1, and I can go ahead and add those together. What we notice is that the -2x and the +2x cancel, so we can cross those off. We also notice that the +1y and the -1y cancel. So that means I have 0 on the left-hand side. That's never happened before. On the right-hand side, we get 3 plus 4, which is 7. Now 0 does not equal 7. And this came up in our solving equations unit. If you ended up with something that was false, we automatically wrote no solution. There are no possible points that are ever going to satisfy this system. So it's a little bit different approach. On the graph, it's very easy to see. You can catch those parallel lines. But when you're working on it algebraically, either by doing substitution or elimination, what's going to happen are your variables are going to completely cancel out, and you're going to be left with something that doesn't make sense. That just means there's no solution. So let's go ahead and look at our next one. For this particular example, we again are going to solve by graphing. So we're going to take our first equation, we're going to get y by itself. What that means is we're going to be subtracting 1x from both sides. And we get y equals -1x plus 3. Our slope is -1, or -1 over 1 if you'd like. And our y-intercept is 0, 3. We'll go ahead and graph this. So you go to your y-axis, you put 0, 3, and then down 1, right 1, down 1, right 1. Make sure you're going down into the right, otherwise you won't get that negative slope in there. Right, we graph our line. And then we move on to our second one. So we're going to do the same thing. We're going to get y by itself. We have to subtract 3x from both sides. So we've got 3y equals negative 3x plus 9. Now we're going to divide everything through by 3. And when we reduce, we get y equals negative 1x plus 3. Now you may think this equation looks familiar, and it does. Our slope is negative 1 over 1. Our y-intercept is 0, 3. When you go to plot this, you're going to be kind of going over the same points here. So 0, 3, and then a slope of negative 1 over 1. So you'll notice that we're actually intersecting at all the points we've already graphed. So what you can do is kind of just add another set of arrows there, or you can graph the line right on top of it, and you're going to notice that, hey, wait a second, these are the same lines. And if one line is directly on top of the other line, they're going to cross at every single point. And since lines have an infinite number of points on them, that's how many solutions we have. So we write down infinitely many solutions. And that's going to be our answer for this. And again, you've seen this before. This came up when we were solving by graphing. So this should be nothing new. The new piece is just going to be looking at it from another perspective. So now what we're going to do is solve by elimination. And again, the nice thing about this problem is that it is set up perfectly for elimination. Everything is lined up. It's just that nothing will cancel right away. So let's copy down our problem again. X plus y equals 3. And 3x plus 3y equals 9. Now, that top equation, if I could multiply that by a negative 3, the x's are going to drop out. So let's go ahead and do that. That's going to give me a negative 3x minus 3y equals negative 9. Now we're set up ready to go. We can go ahead and add that bottom equation that we didn't change at all to the top equation that we multiplied by that negative 3. And what you'll notice is that 3x and negative 3x are gone. But so are the 3y and the negative 3y. So again, we have 0 on this side. But on the other side, the 9 and the negative 9 also cancel. And we get 0. Now that's true. And because that's true, it means that any combination of x's and y's that we plug in is going to work. So we actually have an infinitely many solutions. And I should say any combination of x's and y's that actually fall on the line. So the algebra backs up what we saw graphically. So when you're solving by substitution or elimination and the x's and y's dropped out, you know you're going to get one of our special solutions. It's either going to be no solution or infinitely many. And the way that you decide is if you have a true statement or a false statement. If it's true, it's infinitely many. If it's false, it's no solution. The last thing we're going to finish up with here is just looking at the different forms that we've been dealing with for a linear equation. Now we all know that slope-intercept form is y equals mx plus c. The reason we're coming back to this is you're going to now see a mixture of problems. So it's not going to be obvious whether you should solve by graphing or substitution or elimination. So you're going to have to make that call yourself. For slope-intercept form, obviously it's going to be pretty easy to graph. So a good option for equations that are in slope-intercept form is going to be to graph. But some of you just struggle with graphs and you don't want to graph if you don't have to. So again, you could do substitution because remember the goal with substitution is to get a variable by itself and then plug it into the other equation. So if y is already by itself, it would be a good substitution problem. Standard form, we haven't worked with a whole lot, but you have seen it before. Standard form is ax plus by equals c. And if you think back to your elimination assignments, all of your problems have been set up in standard form. So a good choice if you're given two equations in standard form especially is to go ahead with elimination. So these are just some guidelines that you can use as you go forward and work on your assignment in helping you pick out which method might be the best. You can now stop and begin working on your practice problems.